Hey, welcome everyone to our eighth um, lesson. Today I'm going to be covering a quick overview of BVP solvers, and then which then makes up the last major component of Beluga. So I'm going to return to this kind of rough flow chart of Beluga again. So we have an input script which delivers our OCP and then continuation information. And then I'm just going to kind of combine some steps that were on previous flowcharts. And let's list this as problem conversion. And then that outputs a BVP. And then this is in a numerical form. And then that goes into the BVP solver, which you choose actually in the input script. And then kind of just completing this. We have a continuation handler, which sends information to the BVP solver, and then this iterates around and outputs solutions. Okay, so this is what we're going to be covering today. I'm going to go quite quickly, actually. If we had more time, I'd go more in depth, particularly into like the calculation solver, but just as a matter of not getting too much in the weeds. Also, if anyone's going to work on the solvers, you will need more sources anyway. So I'll just save that for when it comes, if it comes, kind of thing. But in general, we have our two point boundary value problems, which is what Beluga handles right now. This can be extended to 3-point, 4-point, etc. boundary value problems, but in this case we find some y of t such that y dot of t is equal to our defined dynamics, and then we have some boundary conditions like with our optimal control problem. So initial and terminal. If this was a 3-point boundary value problem, like the interior point constraints in optimal control lessons, you would have an internal boundary conditions, etc. So I'm using y in this case. So in this case, in this case, the optimal control problem is collapsed into the boundary value problem such that y transpose is equal to, I'm just going to say y is equal to both x and lambda. So we stacked x and lambda on top of each other. That's why I'm using y as the states and the co-states. And in principle, anything with dynamics, but for our practical purposes, that's the states and co-states. I probably also should have made a new letter for the initial and terminal boundary conditions, because those contain both our original initial and terminal boundary conditions as well as the ones derived with the necessary conditions. Also, as a point, like in Beluga, a lot of times this y also contains the control as well, because you could specify the control with dynamics using index reduction. So we're going to have 3 kind of methods that we can use to solve this, and they kind of work, in my mind, on a continuum. So here we have I guess this is a single shooting method. And then this is collocation. And then I'm going to, in the middle, is the multiple shooting, which kind of bridges the gap between the two. So we're going to start on this left side here. This side, single shooting, or this, what I would say is shooting method. So shooting methods reduce the boundary value problems into corresponding initial value problems. Initial value problems can be solved relatively easily by sequential propagation. So kind of like what you would usually use is like a run cutter, kind of RK, so run cutter 4 or 5 method. That's in MATLAB, that's ODE45 if you ever use it. In Python, that is SciPy solve IVP with RK45 option. There's other methods. So the 4, this is kind of this, because we don't have that much to cover. This is the this is an adaptive method. So like, if I remember correctly, the 4 is the propagation order. So like basically each time step is estimated with a polynomial. The 4 is this with a 4th order polynomial, and well, 3rd order polynomial with 4th order error, and then the 5 is 5th order correction, if I remember correctly. I'm not writing it down, so you don't cite me on that, I guess. But you can look it up easily. So basically, it just denotes the order of the polynomial and the order of the error correction. But so, long story short, the IVPs are easier to solve. You don't have to worry about convergence per se, in that you solve them sequentially. So you solve them in steps. So you first solve like a step from T0 to T1, T1 to T2, etc. And then that's easier than the BVPs. And basically, I'm riffing a lot here. I apologize for not writing this stuff down. But also, you could do that because if you think of an IVP initial value problem, all the information of the problem you have at the beginning. So propagating forward step by step is possible because all the information is contained there. When you go to a boundary value problem, the information that you need to satisfy is both at the beginning and the end. So you have to do it, right? You don't have everything you need to solve it sequentially, if that makes any sense. So back to the notes, the shooting method, steps. Okay, so first we choose values of free initial states. This is initial states and closed states in our problems, but we collapse them all to states. So that's why not. In practice, we kind of choose values for both the free and fixed initial states because in that way it's kind of more generic. But for now, we're just saying if the state has a constraint at the beginning, we know it already, and if the state is, so only the ones that are free to change in the beginning do we choose. And for the first step, it's choosing is a gas. So actually, I'm going to put in parentheses gas here. And then we propagate the trajectory forward to terminal point. And actually, let me draw this out as I'm doing it. So say we have some, this would be a y. In this, y can be a vector, and it almost always is a vector, and just ignoring the bar on top, and then some t. So we'll pick a color. So this will be a y naught here. So that's step one, is we pick y naught, and then step two is that we go propagate it forward. So this would be TF here. And I guess I don't need to cover this anywhere, but as of now, the way we handle TF is fixed. The way our shooting method in Beluga does it is it actually uses, appends time as a state as well, and then normalizes the time to be between 0 and 1. And then you actually find, well, now it actually uses time as a parameter. It's not getting too deep. Basically, we solve time as a multiplier for the normalized time from 0 to 1. So we take all our states, we multiply all the states by the change in time, and then we find the change in time that satisfies the boundary conditions. And with our shooting method solver always propagates from 0 to 1. But in this case, you don't, so time is fixed. Even though if you have a free time problem, we still have a fixed time BVP. So we propagate this forward to the terminal time. And then let's say, I don't know, let me pick a different color. Here, this is where our boundary conditions are equal to 0. Right, so now, so let me label this y naught 0. So then, going back, we propagate the trajectory forward to this terminal point. And 3 is we compute the error in the terminal conditions. So basically this here, and let's call that epsilon for now. That's also before to the residual. So we have some error here. So if error is sufficiently small, we finish the let me just say finish, right? This is an iterative process because else, if the error isn't small enough, we repeat from 1. And we repeat for 1 by correcting this initial gas. So we use this error back here to correct initial gas. So right after this, I'll actually go talk about how we correct. But just for now, visually, right, we need our terminal y to be higher. So then we can go, say this is y naught 1. We can do this, right? And say it does this thing here. And then we have this new error. So then we go in between, let's say go back down a bit, and then say we're really close. We'll take this orange one, not orange, yellow one. So you can see yeah, by changing the initial y, we can hit and that's why it's called shooting. You shoot the trajectory forward like you shoot a basketball. So you get that's probably the best analogy. If you're shooting a basketball, you can shoot the basketball, and if you are too high on the rim, then you can lower your shot a bit. To use a little less force, and then if you're too low on the rim, you use a little bit more force until you get it in the basket. So when you think of it that way, I think it's fairly intuitive. So in that sense, is there any questions, by the way? Okay. So how do we adjust y naught? So we can think of it this way. For a linear system, this epsilon is equal to some desired change. So actually, I guess when I wrote these notes, I skipped a step, right? But the idea is that we want to change this, find the change in this terminal boundary condition, right? So if we have an error, we want it to be equal to some change in the terminal conditions, so it's 0. Well, and actually, we want a step to be the negative of this, but right now, all we have to do is approximate the error. Yeah, so say we have this, right? Actually, let me write it correctly so it's not as confusing. So we have a delta, we want a delta y naught. This is our change to, yeah, so we want it to result in this. So let me just start that way. And since it's linearized, the dy needs to map to this, right? So I guess I'm making it more confusing. Basically, we want to find the dy that does this. So like this is our step, right? And if you bear with me that, so we want some change in phi. If I write this, it should make sense. Right, so we basically compute how, yeah, so maybe that was the right way to write it. I'm sorry, it made sense when I wrote it in my notes, and now it's not. I'm like, oh, this is probably not coming across clearly. So we want to know the change in the terminal by the change in the initial. That's basically what we want. The change in this terminal constraint based on our initial states, because we're guessing our initial states. And that will tell us how much should change the initial states. And then that's equal to the change of the terminal conditions based on the terminal states, and then the change of the terminal states based on the initial states. Right, so this converts to here. And I'm going to find this. This is easy to calculate because this is, I mean, really, actually, this is a partial too. So this is easy to calculate. We have the equations for, this is what we want. And I'm going to call that phi, and then that's the state transition matrix. Okay. So on this, yeah, okay. In other words, we're going to define and then the way this is defined is C goes from TF to, well, it takes in two arguments actually, a final time and an initial time. And then that is equal to how much the final changes, the final states change based on the initial states. Okay. And then let's derive this. Yeah, any questions after that confusing math I just presented? Okay, I guess it wasn't that confusing. So, yeah, because this is not intuitive how to get it right away. And before we proceed, one way is that you could, for every perturbation, you could perturb the initial state, propagate it forward, and see the perturbation at the end, do a finite difference, but that is way too computationally expensive for implementing in a actual solver. So instead we do this, is that, say we have some reference trajectory here, and it will have, I'm going to use star in this case, and this is, so y star of t naught there, and this would be y star of t, and then I'll label this reference. So then we want to perturb it some amount. So, well, let's perturb it here at the beginning. So we have dy t naught. And then this is going to actually be, yeah, y without the star, t naught, and then this whole thing is y of t. And this is perturbed. So we have y of t is equal to some y star of t plus some perturbation dy of t. And then we also let y dot is equal to f of y. So the time derivative of basically the reference plus the perturbation is equal to y dot here. So I guess, yeah, this comes down here. So this expands out because the derivative is linear. So we have y dot star plus dy dot is equal to, and now we use the Taylor series to expand this out because, yeah, just to see how this change affects this function. So that gives us f of y star plus the partial of fy, so the partial of this function with respect to y, evaluated at y star, and that's times dy. And then we have a bunch of higher order terms of function dy. So these two cancel out, right? Because, yeah, y dot star is equal to f of y star. Here we ignore these because it gets small when dy goes really small. So then that simplifies down to dy dot is equal to the partial dy. And then I'm going to say this is, I'm just going to redefine that partial of f of y as f star dy. Okay, so then this above describes the time evolution of a small perturbation in the reference trajectory. But we're still not there. So we know how, a perturbation travels through, but we don't know yet how the initial state affects its final state. So we go back. So here we define the state transition matrix, and you can see it'll end up being the same thing. Well, actually, it's kind of easy to say once I do it. So remember we had something along the lines of this, dy of dy, I should say, of t is equal to, in this case I'm not using tf, I'm just using t because this is true for any time and based on some initial time. So this is defined over an interval. And I'm just going to write that as by just multiplying by ty at t naught, we get so if we go up here, right, this is what I had before here, but instead I use tf. And phi is a square matrix, which makes sense because we are mapping. So y always has dimension, let's in this case say n. So right, matrices map linear spaces. So this is an n linear space, which is mapped to an n linear space. So it should be square and should be n by n. So we differentiate with respect to t. So what does that give us? That gives us dy dot of t is equal to phi dot, and then we get dy of t naught. And so, I don't, let me check my notes because making sure that this is right. Okay, so because t, it's only with respect to t, not t naught. So that's why we don't have a change in this dy of t naught, and it's not dy dot of t naught because this is a constant with respect to t. I just wanted to verify that so I don't teach the wrong thing. And we have the expression for this dy dot of t, which is up here. So we get f star dy of t equal to phi dot of t and t naught dy of t naught. Do a little arrow to show it's changing. And then in this case, we know that, yeah, so we have an expression for this dy of t. If we go up here, or not, we don't need to go that far up. It's defined here, right? So we have f star of phi dy at the initial time is equal to phi dot. And then we could cancel these on both sides. What we get, now we have a first order differential equation for phi for the state transition matrix. What this means is that we could propagate the state transition matrix. Let me actually write this out. With y. So alongside y, we also can propagate this state transition matrix, which is also sometimes referred to like the sensitivity matrix, or it's a sensitivity matrix. But what we need also is we need initial conditions for phi. So you just kind of have to think through this, right? So phi measures this kind of change, right? Well, what is the change of if both of these are at the initial time t naught? So you have phi of t naught, right? So
that's just 0.
It's not 0. It's so what it is dy of t naught over dy t naught. It's not 0, but these cancel. It's an identity matrix. It makes sense because if you're at the same time step and you change, say you measure how much does the change in altitude affect the initial change in altitude affect the final change in altitude. But if you're going forward, no time, they're the same. So it's like how much does altitude affect altitude? It's a 1-to-1 correspondence. So that's the identity matrix. So we have initial conditions for the state transition matrix, and then we have a ODE for it. So we propagate it along. I didn't include this in, I probably spent way too much time on the state transition matrix anyway, but I find it useful regardless because there's other uses for it instead of just shooting methods. You could use it if you're interested in how much some parameter affects the system. You can use it for that as well. So like even if you're not solving optimal control problems, if you want to see how much like an error, say you're propagating systems forward and you are unsure about like basically then say you're flying a plane and you don't know, well, say a space shuttle is coming into the atmosphere, right, and you're not sure of how much there's some error possible in the altitude, you can see how much an error in the altitude will actually determine, like change your final landing location. So it's useful for things like that too. But I'm sorry, I'm in one of those moods where I can sidetrack super easily. But there's also an interesting thing, and I won't go into this in depth, you could prove it, is that phi of t, let's say 2, t naught, is equal to phi of t1, t naught. So you could actually chain these together. So I think the order is correct. Maybe well, we could actually see, I guess I'll prove this right here, is that, so we want, this is equal to dy at t2 over dy t1, t0, which is equal to dy of t2 over dy t1, dy t1, and dy t naught. So I had it backwards. But yeah, it's kind of an interesting, and this actually is a way, well, I'll touch on that in a second. So 2 on 1. So you could actually chain together the state transition matrix, these indefinitely. So you can always decompose them with time steps. And then there's an interesting paper you could look up from a colleague that used to be here at Purdue. Well, it was his master's work. Is he derived a fast shooting method that basically calculated the state transition matrices for each time step on a GPU, and then you could quickly combine them all together just by multiplication. So this actually has uses too. Okay, now, so that was, I won't spend as long on the other two methods. So we have multiple shooting method, and this is going on a continuation. So single shooting, so yeah, single shooting is often numerically unstable. Stability can be improved by decreasing the time errors have to develop. So, yeah.
When you say unstable, does that just mean like you won't converge to a solution?
Exactly. So, yeah, that's exactly what it means. And it comes down to, okay, actually, so let me go back up because that's a good point to hit. If I go back up to this picture here. So imagine that instead of, here when I kind of talked to, right, we did this red and we get an error, and then we use the state transition matrix to calculate sensitivities and correct. But what if that suggested step, which is a linearized step for a nonlinear system, so there's going to be some error in it. And if that linearized step, instead of going, if the nonlinearities are large enough, we should want to go up, but instead what if the step tells us to go down? Then our error is going to get bigger. And then if you, and it's likely to keep getting bigger and actually go away from your target if the nonlinearities on account, the shooting method is based on linearizing the system, and the linearization only holds if it's close, the nonlinearities are sufficiently small. The nonlinearities are bigger over bigger time steps, because it's like the opposite of the extreme case. Everything's linear if you have a really small time step. So you could have this kind of instead of going towards the satisfying your constraint, you instead can go away from satisfying your constraint, and then the numbers just kind of blow up, and you never converge to something. So yeah, when I say unstable, that's what I mean. Is that numerically, when you convert to a solution, it looks almost like a spring mass damper, right, which is a stable system, right? You might oscillate around the optimal, but you'll oscillate around the solution, but you converge to something. So the stability is used in that same way. So it's not stable if you either continually oscillate forever, which is a really edge case, or if you oscillate and the error keeps growing. Like if you have an unstable aircraft system or something along those lines. Does that make sense? Mm-hmm. Okay. So we can cut down on the amount of time for the nonlinearities to grow, and instead of applying the shooting method over a single arc, we divide the trajectory up into multiple arcs. So that's what multiple shooting does. Multiple shooting divides a single arc into multiple smaller arcs. And the principles are all the same here. You can use a state transition matrix as well. But I think it's just best described as a picture. So we have our T, remember we have our Y, and then this is T naught, T1, T2, T3, T4, and TF. And of course, you can have as many as possible. Actually, it's probably best if I make this like n-1, and then n-2, and then do a little like jaggy here. See, we have these different sections now. So we have some initial conditions, so Y naught, and then we propagate that forward. So I'm going to say that's Y naught naught, and then that's Y F naught. And then here we have some Y naught 1, and then we propagate that and be Y F 1. And you can see that we can continue this. And then here we have, the boundary conditions we have to hit in initial conditions over here. So instead of having just this error at the end, we also have an error in between each of these because our dynamics are continuous, or our states are continuous. So not only do we have to match up the error at the end, and the residual at the end has to be 0, the residual between each of the arcs has to be 0 as well. And then the trade-off here is is that the number of things you have to solve for. The shooting method, one of its benefits, despite being numerically unstable often, is that you could define the entire solution with just, Y naught. Like the entire solution could be defined by the values of those 3 states. Now the number, so those are like, I don't know, decision variables or whatever. That's probably not correct because sometimes they use that for control. But basically that's what you have to find. Now you have to find not just Y naught, but the Y that is at each of these arcs. So you multiply, So any kind of correction matrix has to be bigger, etc. So that's the trade-off. Let me actually write that down. So now we need to find not just why not, but why not J for, oh, I guess I used N. So N for, so basically we have to find for N is equal to 1 through, and I guess it's a little confusing, but I think the point comes along. Yeah, so we have more to solve for, but each thing is more linear. And then if we take this to extreme, in extreme case, each arc would only contain a single propagation step. So, and if you, this is a collocation method. So, yeah, if you get to the extreme case, I'm not assuming that you guys know that much about like normal RK4 propagation, but like an RK4-5 propagator actually, as I said earlier, estimates each time step with a polynomial. If instead of taking multiple time steps, but if you kind of divide up your trajectory, and instead of propagating between each time step is only defined with a single polynomial, that's what collocation method. And you could think collocation is like co-location. I think that's where it comes from. I might be wrong, but basically I probably even shouldn't go there. But basically you want to match, instead going from like a propagation and correction thing to a I don't know what tangent I'm going down. I'm in a weird mood, guys. But I was kind of going to go more into math for this, but it was getting too deep for what I want to do. So I'm just going to actually more or less end there. I'm not going to redraw it out because you can imagine if yeah.
Can I just ask you a little bit more about the multiple time step one?
Yeah.
So in this example, how do we come up with our initial like values for like y of t1, y of t2, etc.? All we're given is the boundary values.
Yeah, so actually the way you do that is you guess them as you did before. So imagine in this how the single shooting method, we had to start out with a guess for why not to shoot. This case we need a guess for everything. So not everything, but like a guess at each time step. Likewise for the collocation method, if you take this to extreme and you're only doing like a cubic polynomial between each time step, you still need a guess for each time step for your states. So the way that's implemented in Beluga, which I should turn to showing now after I answer this question, is we will propagate. So in that guess step, when you generate a guess in Beluga, you get a guess for the entire trajectory, and then that is usually in the form of a list of states and a list of times. So as if you use like OD45 to propagate from the beginning. And that's actually what the auto guess method in Beluga does, is that you feed some initial conditions and then you propagate it forward with those initial conditions, and that's your guess. What the multiple shooting method does in Beluga is it actually interpolates. It used to not interpolate, it used to just pick points, but now it actually interpolates for the number of arcs. So say you have 4 arcs that you're doing, it will actually run in as like a cubic spline interpolation to find the estimated value at T1, T2, T3, and then use those as guesses for T1, T2, and T3. Theoretically, you could start them as anything, but it's probably not going to converge. So yeah, the way we usually do it is we take a full trajectory, sample the trajectories at those points, and use those points as guesses. And then that feeds into the continuation kind of thing. So yeah, so you use the trajectory you just solved from the continuation method. I hope that's clear. Yeah, it's once you start getting into, and that's probably why I was originally going to go more in depth even with the calculation method, but it's like if you're going to implement these, which actually if anyone's more interested in Beluga to work on the back end, my plans are to implement an adaptive multiple shooting, because as I kind of laid out here, at least I view like the shooting method then is a continuum with multiple shooting, and then the calculation. Almost all these examples use calculation. If you look into Beluga examples, almost all of them use calculation, so let me open up one of these. It's if I go to the space shuttle one here we just use the SciPy boundary value problem solver specified by BVP, and then that's the calculation one. And we use that because it's just way more stable than our custom multiple shooting solver. But my goal before I graduate is actually to develop a adaptive multiple shooting solver that will smartly choose how many arcs you need, and then we could hopefully get the benefits of both. So if anyone wants to help me with that, then it'll take way more information than I can cover in a single lesson. But yeah, so I'll show you where those stuff. The only stuff are in Beluga right now, but the only example that I know of off the top of my head in these that uses shooting is actually the Bachristochrome problem, and that's because it uses this differential geometry, which I'm not covering. But see, it's a specified shooting here. So let me run that to prove that it works. Yeah, so if you want to see where these are implemented, the SciPy one is implemented through SciPy. That's very straightforward. So, but if you go into numeric BVP, we have a base algorithm, a shooting, and then the SciPy one. So the SciPy one just, with a wrapping around it, just calls solve BVP from SciPy, and then the shooting, is in this algorithm here, but has room to really improve. But this does multiple shooting. It used to do multiple shooting in parallel, which is one of the actual benefits of multiple shooting too, is you can do it in parallel, but you can't really do calculation in parallel effectively. Yeah, so that,
can shooting be faster than the collocation?
In theory, and then that's actually one of my my not frustrations, but goals is I really believe theoretically we can get the multiple shooting faster than collocation. In principle, because the inverting of matrices and it's like less information needed, there's a lot of room to make it faster, and because we could propagate in parallel, the cost of propagation is kind of like should be a fixed cost too. In principle, in practice now it isn't, because this SciPy, the contributors to SciPy have done a really good job on the solve BVP, and in a normal fashion too, when big libraries implement functions, they usually go with the most stable version. So that's why they're using collocation there. If you're using MATLAB, there would be there's a program called BVP4C, which is kind of equivalent to the solve BVP. So both MATLAB and SciPy decided with collocation because it's more stable. And they did a good job writing it because most of, I assume they're like computer scientists and people who write algorithms all day. So in practice, the shooting is slower. And that's why it's one of my goals to really work on the shooting method. And that's kind of, yeah. Before I leave Purdue, I hope to have a fast shooting method that's adaptive and everything. Yeah, that's kind of tangent-y. But if you are interested, yeah, just look in numeric BVP solvers, and there's room to implement more. Beluga in the future can handle as many, right, as long as they interface the same way. And then before we finish up, I guess we have 15 minutes, but so I might run a Beluga problem or two. Hitch also wanted me to show you GPOPs, which I immediately don't know super well, but it's like this is the pseudospectral method. So this is direct method, and I think I'll work with him to make it available. We have a license for all Purdue students, so we can you could run this if you want to do comparisons or whatnot. But just running an example, I've only done this a few times as far as forming my own problems, but it's like Beluga, but it's all in MATLAB. You specify things like Beluga. There's some other things, settings and stuff don't. But this uses pseudospectral collocation and a direct method. So if you're doing work with Beluga, and you want to say, look, my new method using indirect methods gets the right answer, you could in part do it use indirect methods by hand to prove that's the case, and you probably want to do that. But then also GPOPs is kind of standard now, so you could always compare your results to GPOPs. And some examples in GPOPs is shown in like the kind of the fourth lesson. You would get like numerical artifacts and stuff. So if you pick problems in which you have those features, it's a good thing to show, like, look, if you use a direct method, you get these numerical artifacts. If you use indirect methods, you don't. But basically, I don't have much more to talk about GPOPs, except that it's available to us for comparison. I guess it's available to use too if you don't want to use Beluga. My feelings would be hurt a little bit, but I understand it is kind of easier to use now. Yeah, so, and I guess, and this might be assigned, I'm really behind on assigning, like, putting out practice problems, but when I put out practice problems, I think I'm going to include doing this Ali Chan problem in both Beluga and GPOPs, because this problem, I haven't done it yet, but according to Hitch, it does not behave super well. It does not behave well in GPOPs. So this is it being done in Beluga using the SciPy collocation method. And as a side note, so GPOPs uses a method called pseudospectral collocation, which is somewhat different than like the collocation I briefly touched on here in this lesson, because instead of using a single polynomial to interpolate between each time step, actually the calculation that GPOP uses a series of like a large polynomial to interpolate the entire arc, but solves it simultaneously. Yeah, so here's the solution to that problem. It's called the Ali-Chan problem. I think it's just posed to be a tough problem to solve. So there's that. I'm more or less done. And I guess just to finish what I was saying, with GPOP, it uses pseudospectral methods. So it uses Legendre polynomials and special spacing of control nodes. Actually, let me show that because it's kind of interesting, I guess. So this is actually one of the problems that my old advisor, Professor Grant, always kind of went back to too, is so when you so GPOP uses a calculation that you have like a certain number. Let me put a reference function down. Yeah. Right, and say we specify nodes on this evenly. So let's just say every 2 boxes I specify a node. And I use a single polynomial to interpolate this. You get this kind of, so in this case, I probably should have made these, yeah, orange instead, so keeping consistent. You can get this, I'm blanking out what it's called, but this kind of oscillation behavior here. So like, I actually think that's called Runge phenomenon. I'll misstate it if I try to guess. But you get like oscillation between nodes, and it's the biggest at the end because your error, and if you take like a numerical methods class, your error kind of goes up at the ends, and in the middle it's not that high. But you could fix that by spacing nodes differently. So that's like even spacing in nodes, which is like the worst case you can do. But instead, if you space your nodes more at the end, and this is done kind of with an inverse cosine thing, so you have your nodes all kind of grouped up, then it minimizes the error in the polynomial. So you have something that's like oscillates, but the oscillations more closely follow this line. And my drawing is not great. The problem with that, so that's what GPOP uses. In numerically, you have minimal errors. The problem is when you're implementing constraints and things, and like care about like trajectories. The most exciting things in the trajectories happen in the middle, where you have the least spacing of nodes. So if you want to capture that behavior, you end up pushing more and more nodes to the ends of the arcs, because it uses this, and that's. But like Legendre polynomials or polynomials specified to minimize errors with that kind of node spacing. And this is all like extra inning stuff, so don't worry, you don't need to know this. This is to kind of you don't need to know this at this point when you're just starting optimal control stuff. But it's interesting, and I still have time, so I'm going to talk about it. So if we run this. Yeah.
So for those nodes, is there like a dynamic method that would say, oh, we have we have a really big polynomial here that's kind of weird. Let's add another node in the middle here?
Yeah, that's actually, GPOP's claim to fame is the automatic meshing. So okay. It doesn't do it all on one arc either. It will automatically mesh. And so when I talk about adaptive multiple shooting method, I'm thinking of something similar, but you're like use error control terms to pick when to divide the multiple shooting into more arcs. So GPOP does something similar, but with these Chebyshev polynomials, and the meshing is kind of like its claim to fame kind of thing. So it's and when to add more nodes into the mesh. But so here's this I think this one shows a plot of the nodes. If maybe not. Oh no, here. Tell me now. I don't know why it's going so slow. Okay, yeah. So if you look at these plots, well, here's the mesh that started, and see if you look at mesh 1, you could see where it's meshing different points, and then it just kind of builds up. It's hard to see in this problem because it kind of just spits them everywhere. And this is a hang glider problem that actually Beluga can solve too. But as you see how there's these spaces with fewer nodes and then bunches up of nodes. So the bunches of nodes happen at the where arcs meet together, and arc meets together there. This is a lot of nodes at this boundary, etc. That's probably not the best example, but you can kind of see it where it's doing that kind of cosine allocation of nodes. If you go to that same problem, can be solved in Beluga. If you go to atmospheric flight, hang glider, this is one that well, it's taken from this like book of all these different optimal control problems, but it is coded up by Mike Stefani. I think as a comparison. So Beluga is a now 2, takes longer than GPOPs, but it's written in a slower language and fewer people. And plus, Beluga is free and GPOPs isn't. So I'm not. One day we'll get there. One day it will be fast, but it's not. That's why I'm teaching you guys all. Hopefully we can get it there. I probably should have just plotted it because I have the results. Well, I guess I don't have the right results. But I guess in the last few minutes, any other questions, any curiosities? It doesn't have to be about this lesson. We only have 1 week left, and next week is going to be, well, we're going to finish with inequality path constraints, and then the next lesson is kind of, I think it's going to be fun because it's going to be all the like new developments that feed into Beluga. And then we're done with these 10 lessons.
Let me just check for a sec, make sure that everything is on the YouTube channel. If not, I would ask when they would be there. Is everything on the YouTube channel?
Everything but the last lesson. So I'll post this in the last lesson today or on Monday.
All right, thanks.
Sean.
Systems. Yep, we have sessions.
I'll let them ask all the questions and stuff.
Welcome everyone to. I'm sorry, everyone's gobbled together. Can people? Yeah, I'm sorry. It all came goggled.
Sorry. I was just gonna say, once Eli and Wyatt ask whatever questions they were wanting to, would you mind hanging on for just a couple minutes to talk about the task that you gave me?
Oh, sure.
Thanks.
And okay, then yeah, this is. I guess so see, we have the same results as the GPOPs. That's all I wanted to show with this. So yeah, is there any other question? Did Eli and Wright have questions?
Not at the moment, although I'm sure I will in the future.
Okay.
Yeah, not right now. Obviously, if I were to run the examples and look at the code a little more closely, I might have some questions, but not right now.
Yeah, and I was just didn't know when everyone was kind of goggled together. But with that, I hope everyone has a good Friday and good weekend. I'll talk to you next week.